So as we move on through inferential statistics, we basically have two types of things we're going to be talking about. We're going to talk in the upcoming chapter about hypothesis tests, and we'll talk about a lot of different types of hypothesis tests. And then we also talk about confidence intervals. Okay? So in this section, I'm going to talk a little bit about the general concept of a confidence interval, but also specifically about what we call a z-interval for the mean. So what I have to accomplish here is talk about the general idea, talk about kind of the theoretical concept of a z-interval, also the mechanics of how to actually do the z-interval. So there's quite a bit packed in here, and I might have to cycle around the ideas a little bit, but hopefully by the time we get to the end, we'll have a good understanding of what is a confidence interval, and specifically how do you compute a z-interval with or without a calculator if you didn't have access to the calculator. So that's our objectives here. This one, I thought in this section it might be a good idea to really kind of explicitly lay out where we're going here. We want to understand the concept of a confidence interval in general, understand the concept of a z-interval in particular, which is a confidence interval for a sample mean, understand the formula that's used to compute those, use the formula to compute some of those, and then also how to find them more quickly with our calculator. So that's what we're going to be talking about. So we get this familiar picture again, okay? Anytime we're doing inferential statistics, we've got this picture in our mind here. We've got a big population that we can't go out and get all the data from, so we take a smaller sample and we're going to try to use our sample to figure out something about the population. We're going to collect our data, which we call statistics, and use those to make predictions about the parameters. Okay? And so a confidence interval is a way of taking your statistic and building an interval around it to where you have a certain level of confidence, and we'll use probability to specify those things, but we'll have a certain level of confidence that the real parameter is in that interval. Okay? So for instance, we'll take a sample mean, which will be a single number, and we'll build an interval around it that we're fairly confident, like 90% confident, 95% confident, that the actual population mean is in there. And using the sampling distribution, we can actually do that. So that's the big concept of confidence intervals. They wind up having this form here. They're always of a certain form. You have some level of confidence, we call it the confidence level, which typically we might want it to be like 90%, 95% or so forth. And what that means, I'll go ahead and say what that means is if you were to take, using the sampling distribution and the theoretical distribution, if you were to take all the possible samples and create confidence intervals, then that percent of the time you would get one that actually contains the parameter you're looking for. Okay? So if we're talking about the mean, if I were to take all possible samples of a certain size and compute these confidence intervals using this formula you see in the middle of the slide here that I'll talk about in more detail for this particular one, but if you were to do that over and over again and do all of them and say you did a 95% confidence interval, then 95% of the intervals that you made, if you did them all, would actually contain the mean. So that's what we mean by the confidence level, that the procedure used to create one has that probability of finding one that works. Okay? And they always have a certain form. They're an interval centered around the statistic, okay? So around the sample mean if we're looking for a mean. So it's always the statistic minus a margin of error to the statistic plus a margin of error. And the margin of error, how you compute that varies depending on what the statistic and the parameter are that you're looking at and how you're doing it. For the mean, it'll turn out, for the sample mean, we're going to start with what's called a z-interval, which we have the assumption when we do a z-interval that we know sigma. That is a fairly unrealistic assumption because if we knew sigma, we would probably know mu and we wouldn't need this interval. But we have to start with this one because we understand the normal distribution and we can create this interval and we'll understand how it works, and then later we'll replace sigma with s and do something called a t-interval, okay, which is done very, very similar. Once we learn how the z-interval works, it's pretty easy to convert it to the t-interval where we have to use the sample standard deviation to replace the population standard deviation. Okay. So a lot said there, but so a confidence interval is this interval that we have. Again, you pick it and that'll help you find this z star in the formula is called a critical value, and how wide the margin of error depends on your confidence level and so forth. But say you want to do a 95% confidence interval. You will be creating an interval centered around your statistic that you're 95% confident that the actual mean, if that's the what you're looking for, is in there. Okay? And what that means really is that if you were to do the random sampling over and over and over and over again, 95% of the time you would get an interval that doesn't. 5% of the, or get an interval that does. 5% of the time you'd be unlucky and you'd have an interval that it's not in there. Okay? So for the z interval, we wind up with this formula that your confidence interval will be, it's centered around the sample mean, so it'll be x bar plus or minus what we call the margin of error, which for the z interval is this z star, is the way we read that. Z star sigma over square root of n. Now sigma over square root of n, we know from the central limit theorem and from previous sections, that's the standard deviation of x bar. And z star is the value that you go out to capture a certain percent of the standard normal distribution. By multiplying it by sigma over square root of n, you're finding how far you go out in the regular normal distribution, or in any normal distribution based around mu and sigma over square root of n. So that's the formula. There are some conditions that we need. Anytime we start doing inferential statistics, we have some assumptions that are going on that we should check here. First of all, when you do inferential statistics, you're using probability based on random sampling. Okay? So we are assuming we have a simple random sample with no response, no other practical difficulty. If we don't, then the probabilities we're assigning are not really accurate because we're basing them off of random sampling. Okay? We're also assuming that the variable we measure has an exactly normal distribution with mu and sigma as the mean and the standard deviation. We do, however, have the central limit theorem going for us that x bar would have mu and sigma over square root of n and be approximately normal, which helps us when we do the sample means in particular. And then the big assumption that probably is not going to be the truth in real life, and we're going to have to switch to a t interval in the next sections. But we assume we know sigma starting out so that we can use the regular standard normal distribution that we've talked about so far. Okay. And again, just to remind you, the normality, we're usually okay. If we have large enough sample sizes, we don't have to worry about that as much when we're doing the sample mean, because we know if you have a sample size of at least 30, the central limit theorem kicks in and x bar would be approximately normal with a mean of mu and a standard deviation of sigma over square root of n.